Thanks for listening. I'm recording in front of my lovely class. Recorded for future posterity. All right, so first question. We got this motor that is doing a bunch of work on this block that is at rest at the bottom of the ramp. It's at rest, it's not up. So all the energy of this block is going to come from the work done by the motor. And we have this graph here that's a force distance graph. And what do we do with the force distance graph? Force times distance is work. So area under the graph is going to be work. Now, two ways we can solve for that. We can either break it into a rectangle and a triangle and add up those areas. But my personal favorite way is to find the average force and just multiply it by distance. What happens to be smack dab in the middle between 50 and 65 is 57.5. If you're having trouble figuring that out, remember average of two numbers, you just add them up and divide by 2 equals 50 plus 65 over 2. That's how you find the average of any two numbers. So in this case, I'm going to say, hey, my work is equal to my average force times distance, which is 57.5 times 10. So we have 575 joules of work done here, and that's going to provide potential energy, kinetic energy, and create a little bit of thermal by the end. Which brings us to the next question. If 150 joules of heat energy is produced through friction during this 10-meter pull up the ramp here, what's the final speed of the crate? So we started with this 575 joules that the motor gave to the crate. So it did that much work, and that's going to become potential energy, kinetic energy because it's moving, potential energy because it's up, and thermal energy, the 150. So 150 of the 575 has become thermal. So we're going to do mgh plus 1/2 mvf squared plus 150. What is our mass here? It is 10 kilograms, and it goes up 4 meters. So we have 575 equals 10 times 9.8 for g times 4 meters plus 1/2 times 10 times whatever our final velocity is, which is what we're looking for, plus 150. 9.8 times 4 is 39.2. 39.2 times 10 is 392. 1/2 times 10 is 5, plus 5 VF squared, plus 150. Oops. All right, so at this point we've got 575 joules of initial energy has become 392 joules of potential energy, 5 times the final velocity squared of kinetic energy, and 150 joules of thermal. Math it up, solve for VF squared, you're all done. This next guy here, we'll again start with before equals after. All your energy is coming from the work done by this 50 Newton force exerted over 3 meters. So you have this 10 kilogram block, it's pulled with 50 newtons for 13 meters. Friction is going to do 380 joules of negative work, or you can either think of friction doing negative work on it, reducing its energy, or you can think of it as 380 joules of thermal energy was created through friction, which is how I'm going to approach it. So I'm going to say, hey, before we got a bunch of work, that's going to become a bunch of thermal energy. That's that 380. And all the rest that's left over is going to be kinetic. And so we'll just do force times distance is work. Force times distance, we got 50 times 13, which is 650. And that's going to equal 380 plus 1/2 times 10 times VF squared. And 650 minus 380 is 270. So 270 equals 5VF squared. And VF will just equal 7.3. Next guy. We got pushing a crate across a smooth wood floor with a constant pushing force. One of your power formulas is power is equal to the force you're exerting times your velocity. This guy, if it's accelerating, this guy is increasing. And our force is staying the same. This is constant. What do you think you get if you get an increasing number multiplied by a constant number? I think I'm going to keep getting a number that's going up and up, which would make my power increasing as well. Notice there's nothing that's going to make it constant because we just have this. It's just a number being multiplied by something that keeps getting bigger and bigger. So our answer is just increasing. Next guy. We've got this steel ball like it's being launched from some little cannon on the ground. So let's say it's basically on the ground, moving up at 280. And then sometime later, it's up at some height. And it's hotter. It's got some thermal energy too. So this is kind of your before side. Here's your after. It's launched from the ground at a certain velocity, and later on it's up and hot. So we're just going to do before equals after. And before, we got some kinetic energy. It's basically at the ground. So it's just 1/2 mv squared, and all that energy we had in the beginning, and kinetic energy, some of it's going to become potential energy, and the rest is going to be that thermal energy that we're told. So we got 1/2 times 45 times our initial velocity, which is 280 squared, and that's going to equal 45 times 9.8 times our height, which is what we're looking for. Plus our thermal, which is 8.5 E5 times 10 to the 5. I'm not going to math this because I'm trying to do this quickly. But yeah, solve for H using algebra. Next guy, we want to do a graph of EK versus time for a ball dropped off a roof. Now its velocity is going to look like this. So every second it's getting 9.8 meters per second faster than it was the previous second. So you've got a constantly increasing velocity with time, but our formula is 1/2 mvf squared. So our thing that's directly proportional to time, our velocity, is getting squared. What does a y equals x squared look like? A graph look like? It looks like this guy. And because our thing that's directly proportional to time is getting squared, we're going to have like something that looks like a y equals x squared graph. Next guy is much simpler. We're looking for total energy. And the big thing with energy, the whole reason we can do before equals after, is if we're tracking all the different types of energy, including like thermal and all that, it just stays constant. It's the same all the time. Energy is neither created or destroyed, it just changes forms. So this is their guy. You just got a constant total energy that is not changing. You might have more potential at one moment and less kinetic, or vice versa, but if you add up all your different types, it'll maintain the same total. This next guy here, this one, if you think about it for a minute, isn't too hard. We're pulling this block of mass M, distance d across the concrete floor. What happens if we make the surfaces rougher? What if it's we got more friction going on? If we got more friction going on, it's going to be slower, because more of that energy is going to be dissipated as heat. So our final kinetic energy will be less, and our heat energy is going to be more. One way to think about it is our thermal energy is equal to our force of friction times distance, or mu Fn times distance. Apologies, it's breaking once again. And we're back. So yeah, if we increase mu and everything else stays the same, we're going to increase our thermal energy created. We've got a given amount of work that's going to become thermal energy and kinetic. So if we increase our coefficient, if we increase our force of friction, we will increase the heat energy created, but that means we've got less energy left over from our work to be kinetic. Next guy, we got this one. I would recommend, I always like making my zero height the lower of my starting position and my ending position. Whichever one's lower, I just make that my zero height. So I'm going to ignore this whole 15 business. I don't need it. So if I consider this to be at zero height, it's got no potential energy initially, and I'm going to do a before equals after, and it's going to freeze again, and I'm going to hate my life. All right, hopefully you can see me now. All right, so 4 equals after, and before we got kinetic energy, so we got our 1/2 mv squared, and afterwards it is up and moving. So afterwards we got mgh, and I'm going to list it as ek, because we are looking for the kinetic energy at point P. So I could find the velocity here, but I don't need to. I need to find this whole thing. So I'm just going to solve for that whole thing. So I'm just going to go 1/2 times 1.2 times 16. So 1/2 1.2 times 16 squared equals 1.2 times 9.8 times 4 plus EK. Find this whole thing and then subtract this whole thing, and you got it. That's it. So whatever 1/2 times 1.2 times 16 squared is minus 1.2 times 9.8 times 4 is, that'll give you your potential energy. All right, or sorry, kinetic energy at point P. Next guy, we've got this aircraft. It starts out on the ground, not up, not moving. This has got no energy in the beginning. We want to find minimum average power required from the aircraft's engines during this time to go from on the ground and not moving to up in the air and moving fast. And so we're just going to use this formula. Power equals change in energy over time. And you just got to ask yourself, did it get more up? If so, we're going to throw in an MGH term. It did increase, its height increased by 9,500 meters, but it also got faster. So its energy, kinetic energy also changed. It started with 0, and now it's got 1/2 m times 210 squared energy. And then if we want to find the energy per second, how much it's changing per second at least, or we just divide it by 920, the number of seconds. Now, the reason it says minimum average power is if you get a plane from the ground up in the air, there will 100% be friction and all that. So it's saying, like, in a perfect world, what would be the very minimum you would need? And the very minimum would need to be to give it this much potential and this much kinetic if there was a perfectly zero friction world. So yeah, just 5,500 times 9.8 times our height, because that's how much it changed by. Notice this should be change in energy, so final minus initial. This is our final. Our initial is just 0, so there's an implied like -0 here to make it change in energy, because it starts off not up and not moving. Okay, so there's our potential plus our kinetic, which is 1/2 times 5,500 times 210 squared all over 920 to change it from work to power to get joules per second instead of joules. And that's it, whatever that happens to be. Next guy, we got a force distance graph. Make sure you can handle this. Nothing too crazy though. Anytime your y variable times your x variable is something useful, area under the graph is that thing. And just like I mentioned at the beginning of this video, by the way, we want to know the area under the graph from 0.2 to 0.8. 0.2 to 0.8. That gives us a base here of 0.6. And the way I like to solve for this, you could break it into a triangle and a rectangle. So find the area of this rectangle, add it to the area of this triangle, and you get the area. But my favorite way is just to kind of like in my head, take this triangle, move it right here. So I got a big rectangle of exactly the same area as the original shape. This is effectively what you are doing when you are doing average force times distance. Now, the number that is smack in the middle of 4 and 16, the middle number, the average number, 4 plus 16 divided by 2. The way you find the average of two numbers is add them up and divide by how many you got, is 10. So we have an average force of 10 newtons, and we're exerting it for 0.6 meters. So I'm going to say my work is equal to my average force times my distance. So 10 times 0.6 is just 6. And there we are for that guy. We've got a very similar plane question right here. Only in this case, we want minimum work instead of minimum power. So again, work is change in energy. And in this case, just like before, our plane starts off at rest on the ground. So it starts with no energy. So when we do change in energy, final minus initial, our initial is just 0. So I'm not going to write it down, but there's this implied minus 0 when we're finding the change. This plane started off stopped, started off on the ground, and now it's both up and moving. So our change in energy is mgh because it got higher in the air, more up, plus 1/2 mv squared because it got faster. So we'll just do our mass, 1,500 times 9.8 times our height, 3,200, 3.2 kilometers. Plus 1/2 times 1,500 times our final velocity squared. And that is how much our energy has changed, and that'll get us the minimum work. In real life, of course, the engine's going to have to overcome friction and have various other inefficiencies. Next guy. We got another force distance graph. So we want to find work. Work is force times distance, and so if we got a force distance graph, it's also equal to the area underneath that. And we're interested in the area between 0.4 and 0.6. Middle number between the starting force of 8 and the ending force of 12 is 10. This is our average force. And our distance we're pushing for this interval from 0.4 to 0.6 is 0.2 meters. So I'm going to say my work is equal to the area under the graph, which I'm using average force times distance. So that would be 10 times 0.2, which is just 2. Next guy. We want to do efficiency. So I see no power here, no time. I'm going to do the efficiency formula, which is equal to what you accomplish, your work output, divided by what you put in. Now, what we put in is what he expended, this many calories. Remember, a calorie is the same type of unit as a joule. They're both units of energy. So in expending this much chemical food energy. He managed to increase his potential energy. If he's climbing up, what he's accomplishing is increasing his potential energy. Workout is his change in EP, which is equal to just mg times your change in height. 490 minus 250 is just equal to 240. So we've got his mass, 75 time for M is 9.8 for G. And then the change in height, how much his height has changed to find the change in energy, is 240. And then we just divide by how much energy burned, how much food energy. So 2.8 times 10 to the 5. Next guy. We got this change in kinetic energy. Change in energy is just work. So done. Change in energy is always just work. Change in kinetic energy is technically work done by the net force. Net force causes acceleration. Accelerations change the kinetic energy. Work is change in energy. Work done by the net force is change in kinetic energy specifically. Not that you need to know that for this. 16 kilogram object is dropped from a height of 25 meters and strikes the ground with a speed of 18 meters per second. How much heat energy was produced during the fall? Again, we got a before equals after. Before, we've got a bunch of potential energy, and it's becoming kinetic energy at the end right before it hits the ground, plus a bunch of thermal. And so we just do our MGH, 16 times 9.8 times 25. That's going to equal 1/2 times 16, our mass, times our final velocity, which is 18 squared, plus E thermal. So all we're going to do to solve for this is take this guy and subtract this guy, and then we'll have our thermal. That's it. Next one, we got this guy. We got another force distance graph. I wonder what we do. Force times distance, or y times our x is something useful, so the area under the graph is that thing. In this case, we can't do our average force thing so easily, so we're just going to find the area of this triangle and the area of this rectangle and add them up. 20 times, area of a triangle is base times height divided by 2. Base times height over 2 is our area. Our base is 10. Our height is 20 over 2. 10 times 20 is 200. Divided by 2 is 100. So we got 100 joules from this area. And then this distance is 5. So we got 20 times 5 is our area of this rectangle here. 20 times 5 is 100. So we got another 100 joules because of that rectangle, leading to a total. Our work is 200 joules total. 100 for the first 10 meters and 100 for the next 5. Work is equal to change in energy, and this net force is causing a change in kinetic energy. So 200 joules is going to equal 1/2 times our mass times our velocity squared. 200 divided by 4 is 50. 1/2 of 8 is 4. So we got 50 equals V squared, and then V is going to equal 7.1. Just a little bit over 49, so it's going to be a little bit over 7 for the square root. You got this guy, everyone's favorite question. So all you got to do for this guy, trick is your potential energy is going to become horizontal kinetic energy here. So we're trying to figure out, hey, if we bring it twice as high, how much faster is it going to be here, and therefore how much further horizontally is it going to go. Now, if you remember kinematics, I told you how horizontal components have no effect on vertical things. So regardless of how fast it's moving horizontally here, your initial vertical velocity is 0. So it's going to take the same amount of time to fall this distance here. So our time is set, and our distance is equal to our horizontal component here times the time. This is constant. So whatever happens to our velocity is what happens to our horizontal displacement. So all we got to do is figure out, hey, if we take it twice as high, how many times faster is it moving here? So that's what we'll figure out. And however many times faster it's moving here is going to be how many times farther it goes horizontally. So here is what I call let proof. First of all, I'm going to come up with a formula for my velocity here, and all I'm going to do for that is before equals after. So we're going to have mgh. We got a bunch of potential energy in the beginning, and it's becoming a bunch of kinetic energy down here. I got m multiplied by everything on both sides of the equation, so I'd cancel it. Multiply both sides by 2. I got 2gh equals v squared, or v equals 2gh square rooted. Now, here's where the magic happens. I'm going to say, hey, before, my velocity before, when it was coming from, dropped from a height h, I'm going to say, let my velocity before just equal to the square root of 2gh, whatever g and h happen to be. G, we probably know. I'm going to say v after is equal to root 2 g times 2h. Now the trick to these proofs is I want to pull out any differences, and the only difference I've got between this velocity before formula and this velocity after formula is this 2 here. So I'm not going to multiply it by the other 2 or collect like terms or anything. I just want to separate out any of my differences and end up with a formula that is equal to the difference times the original formula. This equals that. I just moved out the difference. And the reason I want to do that is I want to replace this formula with what it's equal to. This formula is equal to the velocity as it was when I lifted at a height h. Now that I've lifted at a height 2h, it's root 2 times that formula, or root 2 times the velocity before. Because we said this formula is equal to the velocity before. And because of my little logic here, since our time in the air is constant and we're just messing with velocity here, whatever we do to this velocity, if we double it or triple it, we will double or triple our horizontal displacement. In this case, it turns out if we bring it twice as high, we're going root 2 times as fast. So we're going to go root 2 times as far. And so that gives us our answer. Hopefully that makes sense. This is the first time you're running into it. It'll get easier with practice when we see it in future units. Anyway, hopefully this was helpful. I got to go for now. Thanks for listening.